Welcome to the first video in Module 5 that deals with numerical differentiation. So why do we care about numerical differentiation? Because differentiation gives us the rate of change of a quantity, and that is key in many engineering applications. So here is an example. Take, for example, the position as a function of time. So x, the position, is a function f of time. So here's an example in this graph of this position. Now, if we're interested in the velocity of this object that has the position x, what we would do is we would take the derivative of this function in time. So we would take df dt. That would give us the velocity of an object as a function of time. Now, furthermore, if you're interested in the acceleration of this object, then we would take again the derivative of the velocity function. That would give us the acceleration. But then the velocity itself is the derivative of the position. So therefore, the acceleration is really the second derivative with respect to time of the object's position. That's shown here as an example as well. So if we know the analytical form of this function f of t, and we know how to actually do the analytical differentiation, so we know the analytical form and we know enough math to perform an analytical differentiation, well, that's great, then we're all done. But more often than not, we don't know the analytical form of the function f of t, or we don't really know how to calculate the analytical derivative. So here are some examples of these cases. A example, we may only know the value of f at a set of discrete points, so we actually don't know the actual analytical form of f of t. Or we may know the analytical form of f of t, but not its derivative. So in this second case, if we know the analytical form of f of t, we can use this to calculate discrete data points, and then we can revert to this example A, because now we have discrete points of the function that we will then use to calculate the derivative. So because both cases can be brought back to finding the derivative of a function that is given as a set of discrete data points, that is the most general case that we will look at in this module. So in general, there are two approaches for the numerical approximation of a derivative that is given by a set of discrete points. The first one is called finite difference approximation. There we estimate the derivative of the function f of x at a discrete point xi using points in the neighborhood of this point xi. So that could be neighbors to the right or to the left of this point xi. So shown here is an example in this graph where we have a point xi where we want to evaluate or approximate the derivative, and we would use points in the neighborhood. So for example, xi minus 1 or xi plus 1 and the function values there to estimate the derivative. The second approach is called curve-fitting approximation. And the idea here is to first curve fit an easily differentiable function to the points in the neighborhood of xi, and then to evaluate the derivative by doing the analytical differentiation of this fitted function. So here's an example where we have discrete data points representing our function, and we first calculate a fit to those data points using the methods that we learned in a prior module. And then we do the analytical derivative of this fitted function to approximate the derivative at the grid point xi. Thank you for watching.